Now let's take an actual chemical reaction and apply the principles that were introduced in the previous video. Here we have 2 moles of nitrogen dioxide decomposing into 2 moles of nitrogen monoxide plus 1 mole of oxygen gas. And initially at time 0, we have 0.0100 molar NO2. Okay, and there's 0 moles of the nitrogen monoxide and the oxygen. So as this reaction progresses, the nitrogen dioxide is going to decompose, and that concentration is going to get smaller. So if we do a plot of concentration versus time, so we'll put concentration on the y-axis, time on the x-axis, and if we look at what happens to the concentration of NO2 as we proceed, we're starting with 0.010 moles, and as we go down this column, the concentration is getting smaller. So what happens is we have a drop off in the concentration as we progress with the time. So this right here is going to be the concentration of NO2. Okay? If we were going to represent what happens with the concentration of NO, we see that we start with 0.00 molar, and we progressed to 0.0062 molar. Okay, so we're going to start down here at 0, and this concentration is going to increase as we proceed with time. So this will be the concentration here of the nitrogen monoxide. In addition, we're going to look at the concentration of O2. The concentration of O2 starts out at 0, and it ends up being 0.0031 molar, okay? Which, if you look here, is half of the concentration of the NO when we get down to 300 seconds. So what we're going to see with this is we're going to see a curve that kind of goes up like this. And this is where we're going to end up with our concentrations as we progress through with time. Okay, so the concentration of the O2 and the NO are going to increase. The concentration of the NO2 is going to decrease. So when we kind of go and look at these together, we can look at what the average rate is. And the average rate is going to be the change in concentration per change in time. Okay, so if we looked at the NO2, we're going to start with 0.010 molar and go to 0.0079 molar. So these two data points right here. Okay, so the change, remember, is the final minus the initial. So we're going to do 0.0079 minus 0.0100. That's going to be divided by the final time, which is 50 seconds, minus the initial time, which is 0 seconds. If we do the math here and come up with an expression, we're going to get negative 4.2 times 10 to the 5th molar per second. Okay, so there's a couple things that we need to introduce here. First of all, this rate right here is negative. Okay, if we look at miles per hour in your car, you really can't have a negative rate. But we use this sign convention here to indicate that this is a rate of disappearance. Okay, and this is the change in the concentration of NO2 per time. All right, so remember from the previous example we went over rate of appearance and rate of disappearance. So if we compare this, so this is going to be rate of disappearance of NO2 per time, and the units we typically express are molar per second. All right, if we were going to compare these, we have a coefficient of 2 in front of the NO2, and we also have a coefficient of 2 in front of the NO. So since we have a 1-to-1 mole ratio, the rate of disappearance of NO2 is going to equal the rate of appearance of NO. Okay, so both of these are going to be the same with the exception of we have a different sign. Okay, and if we look at this, the rate of appearance of the O2, so if we look at rate of appearance of O2, that should equal 1/2 the appearance of NO, because we have a 2-to-1 mole ratio here. So the coefficients here, if there is no coefficient, it's the same as a 1. So we have a 2-to-1 ratio, so that's going to affect the rate at which the oxygen and the NO appear. And as you can kind of see here, initially we start at 0 with both of them, right? And we have 0.0011 and 0.0021. So this is roughly half of what this other value is here, right? 0.0018 and 0.0035, 0.0026, 0.0052, 0.0031, and 0.0062. So as we progress, and if we collect our data properly, we're going to see that the rate and the concentration that we end up with is directly proportional to the stoichiometry of the balanced chemical equation. Okay. Another thing that I want to kind of focus on in this graph right here, right? So if we focus on this, we can say that rate is not constant. It decreases with time. Okay, so the rate at a particular time is the instantaneous rate and can be obtained from the slope at a point. Okay, so we can calculate an instantaneous rate, and if we would be using differential calculus, we would look at instantaneous rates of change, but we're going to do a lot of approximations here in this particular class, and we can determine then the instantaneous rates at any particular point. Okay, the initial rate is the rate of the reaction when the reactants and products are first brought together. And this is at time t equals 0. Okay, so and we can find the slope of that tangent line at t equals 0. So these are some different ways that we can look at rates, and I want to make sure that you guys definitely know how to look at some experimental data, figure out how this plot would go, and notice that these aren't linear trends that we see. These are more exponential trends, and they're not, you don't see constants here. And the rate can definitely change. So we're going to investigate how to try to interpret plots like this in a better way, in a nice, easy, straightforward way. And we're going to introduce in the next video something called rate laws, which will help us understand what's going on in these particular rate expressions.